Hello, sir.
Hello Karthik, can you hear me?
Yes, sir, I can hear you, sir. Good afternoon, sir. Uh,
Afternoon.
sir, if there's some time left out today, sir,
Mm-hmm.
uh, can you explain the position regulator equation, sir? Like how uh, how did we get F net is equal to minus KPX minus KVX dot, sir? The concept of that.
Hmm.
Briefly, you can explain, sir. I do have some idea, but just I am having a little confusion. Could you briefly explain, sir, if there's some time left out today?
Yeah, sure.
Yes. You got it, no, sir, what I was
Yeah, I got like I was planning to cover a few things before I discuss that in detail. So I will be going to discuss that in detail.
okay. Yes,
Uh,
sure, sir.
and
Go according to your plans.
yeah, maybe if not in this discussion hour, then surely in next discussion hour, but I will discuss that.
Sure, sir, sure. No problem, no problem.
Okay. Okay, so let's get started. In the last week, we talked about second order differential equations in context of the designing controllers and representing systems, and we use the spring mass damper system uh, for understanding what are the different scenarios then could arise by varying the parameters such as stiffness and damping. And we saw the responses also, responses like in which case the oscillations happen, in which case oscillations die down the fastest, that is the critical damping. So till now the discussion was mostly like it it couldn't be considered as entirely as a mechanical discussion also, like this could this there was no special focus on how it's related to control, or how will these systems come into the picture when we are designing controllers for some application. So now we'll take a step towards that, and I will talk about stability, how to basically using few there are ways using which we can comment on the stability of the system. And once we can comment about the stability of the system, then we know that we have a criteria based on which we can design our controllers, because in the end we want our controllers to make our system stable, to drive the error to zero, right? So I will pick off from where we left the second order system. So what we saw was that we have a spring mass system, and the equation of motion of such a system turns out to be a second order differential equation. And till now we were considering homogeneous equations in which there is no external forcing, but in a general scenario there can be an external force on the system also, an external excitation, right? And this is the stiffness and damping, this is the support. So the general equation will be written as mx double dot plus bx dot plus kx is equal to f. Now the equations, the form of the equation that is currently being written, it's in the what we call as the time domain, because all these parameters we have like xt, x dot t, so the states, the derivatives, the accelerations, they all are function of time in this equation. But very often these equations are converted into what we call as the frequency domain. using the Laplace transform. So I think this was Laplace transform has been introduced in the lectures briefly, and I will also go over it once. So Laplace transform, what it does, it converts from time to frequency. So for a function, now little bit of maths, just brief. Any function, if there's a function f as a function of t, then the Laplace of that function is given as this integral e to the power minus st ft dt. Right, so this is the expression which you can use to find the Laplace transform of any given function ft. So in the time domain, the variable, the independent variable will be time, and in the Laplace domain, it will be s. So commonly used notation is s. So there is a table of of common functions and their Laplace transforms. You can check it out. So check out the so you need not integrate, do this or evaluate this integral every time you encounter certain function. You will be most likely using the transformations from the table, like what about sine t, cos t, and common functions. But we won't be discussing that. What we will be discussing is we will be concerned with few small formulae. That is, first is Laplace transform of the differential of, let's say, y. Okay, what is that? So that is written as and for y double dash t, it is s square ys minus s y0 minus y dash 0. And here, what is capital Ys? It is the Laplace transform of only yt. So if this is known, then we can write these two expressions, and of course the initial conditions. So what we will assume right now is that the initial conditions are all 0 for just easier bookkeeping, and what we'll do is we will take the last Laplace transformation of the differential equation we wrote above. Right, so this turns out to be, if we use the above relations, then it will be ms square xs plus bs xs plus k xs is equal to fs. So taking xs common, what we get is ms square plus bs plus k equal to fs. Now if we just switch the terms, then the ratio between the response, that is the x, and the input, that is f, the relation is given by this expression on the right hand side of this equation. And this type of relation, sorry, this type of a relation, this is called as the transfer function, right? So we get a relation between the input and the output, and these relations, for the systems for which we can clearly write these relations, that expression is called as the transfer function. And this function is very important because analyzing this function gives us an idea of what will be the response of the system, the behavior of the system given certain inputs, right? So the following discussion will be around the analysis of transfer function, and for again ease of understanding and their common occurrence, we will limit ourselves to these second order systems, because these are the most common systems that you will encounter. So what we have seen is that the spring mass damper system excited by an external force can be modeled as a process in which the input is the excitation, the output is the position of the block, right? And those two are related via this transfer function. Okay. Now, before I start the analysis, I will just briefly draw a diagram commonly used in controls literature. It's the block diagram of a typical closed loop control structure. So let me just draw it once and then I will explain. Okay, so this is the I will here use x as the input and y as the output, so just don't get confused with the x in this expression. So we have the input, we have the output, and there is a process in between. What we like to find out is what is the relation between the input and the output. So basically the ratio of ys and xs, that is the transfer function. So for this very simple block diagram, what is the transfer function? And practically what is happening in the system is that this connection from here, right, this from here, we are taking ys, which is the actual response of the system, multiplying it with some function hs, and then feeding it back again into and comparing it again with the input, And again, based on some logic there, that is GS, we generate the new output, right? So what's coming in here is ys times hs, right? Because ys comes from here, multiplies with hs and reaches here. Input is coming xs, right? So if I just denote es here, so es is xs minus ys hs. And now the second thing that you can write is es times gs is ys, right? Because es goes into gs and then it becomes ys. So this is also valid. Now in both these equations, so if you replace the value of es from the first equation into second, if you replace the value here, then what you will get is, I will just drop the dependency on writing bracket s everywhere, but just remember that there is a dependence on s. So x minus yh times g is equal to y. Now once you get this relation, the only thing that is left is to bring y and x on one side and other terms to the other side. So just expanding, you get gx minus yhg is equal to y, that is gx is equal to 1 plus gh y, that means y by x is g by 1 plus gh. So this is the transfer function. Any doubts in this? Okay, so block diagrams are a very common tool for laying down the system, the plant and the controller, and there are a few block diagram simplification techniques also, but we will not go into that here. What we will see next is that once we have the transfer function, then how to analyze it. So there are a couple of interesting things which you can actually think whenever you see a function, and that is that when that function goes to 0 and when that function goes to infinity, or basically goes unbounded. And transfer function generally, as you see, is a ratio of two functions, two polynomials, right? And if the numerator goes to 0, then the entire transfer function goes to 0, right? And if the denominator goes to 0, then the transfer function blows up, it goes to infinity and becomes unbounded. So the two things which we will find out about this any transfer function is when does it go to 0 and when then does it go to infinity. And we are more concerned with the second one, because this is what we try to avoid. We don't want our systems to go unbounded, because then they will be unstable, and in reality accidents or some damages might happen. So this g by 1 plus gh, so this is a polynomial of some degree. This is a polynomial, so let's write it as like some function of s and some function of s. This is the numerator, this is the denominator, right? Now there's a term called as a proper transfer function. So proper transfer function is that when the degree of polynomial in the numerator is less than the degree of the polynomial in the denominator. And we will see why uh, this is important. So most of the transfer functions which you will see will be will satisfy this criteria, right? And this ratio, when it will go infinity, when ds is 0, right? So ds is equal to 0. this this equation that will be formed is called the characteristic equation, right? So for this, for a transfer function like this, the characteristic equation is 1 plus gh equal to 0. Now this is a what? This is a root finding. We have to find the roots of this, right? Because we want to know that what are the values of s where the denominator will go to 0, right? And so characteristic equation is also abbreviated as CE, and roots of CE, that is characteristic equation, are called poles of the system. Okay. And setting the numerator equal to 0, this will give roots, and they are called as zeros of the system, because on on those values of s the response will be 0. Any doubt in the definition of poles and zeros? Okay. So now the first thing which you will do when you get a transfer function is find out the poles and the zeros, right? And the transfer function is most, as I said, is written in the s domain. So we will plot those poles and zeros in the s plane, right? So this s is coming all the way from the Laplace transform which we discussed at the very beginning. So we have the s plane. So it's again same as the 2D space, just difference of notations. So here we plot the real components, and on the y-axis we plot the imaginary component. So this is a complex plane, right? So any complex number can be plotted on this, and yeah, this is the origin. This is called the right hand side plane, RHP, and this is the left hand side plane, LHP. Okay, and this is the imaginary axis. And this is the real axis. So any pole or zero can be plotted here, right? So a notation is that poles are represented by a cross, and using a circle we represent zeros, right? So just remember this notation, that will be useful for the subsequent discussions. So poles and zeros can be plotted in this plane, right? Now at this stage we will tie up what we had seen in the previous discussion hour about the damped, uh, critically damped, underdamped, overdamped systems, and the same thing how they relate to poles and zeros of a second order transfer function, right? So the analysis, the outcomes will be the same, but we will see how the same conclusions can be also arrived at using the root of transfer functions. So the transfer function that we had computed for the second order system is this one, right? And let me rewrite this. So second order transfer function, that was, and let me denote it as ts, that was 1 by ms square plus bs plus k. The more common way to write this is in terms of two parameters, the two key parameters which we had discussed last week, the natural frequency and the damping ratio. So we divide by m, and what you know that we define omega n as root k by m and xi as b by 2 under root km. So you can very easily see that you can write it in an equivalent way using damping and natural frequency like this. Okay, so I will rewrite it once again. Okay. Oh, my bad. All right. So this is the typical transfer function, and the characteristic equation will be s square plus 2 xi omega n s plus omega n square is equal to 0, right? This is a quadratic equation, and the roots of such equation you have seen in the last class. So s can be written as minus p plus minus under root b square minus 4ac by 2a, that is 2. So this will be minus xi omega n plus minus, and this will be omega n into xi square minus 1. So this is s1 and 2. These are the poles. What are these? These are the poles. Now, once we know the poles for this second order system, the next thing which we need to do is to plot them and comment that when the system will be stable or unstable or will have oscillatory behavior, right? So let's get on to that. So first let me draw this out for a general uh, case, and then we will analyze. So in the S plane, here note that if you see that there is under root xi square minus 1, right? So interesting things happen whenever there is a difference in under a square root, right? So if xi is greater than 1, right? So remember that when xi is greater than 1, system is overdamped. Then both the roots will be real, right? But when xi is less than 1, then there will be an imaginary part in the roots, so roots will be complex, right? So if xi is greater than 1, then real roots, or I should write real poles, and if xi is less than 1, then complex poles. And important point is that complex poles always occur in pairs if the coefficients of the polynomial whose roots they are, those coefficients are real, right? So the point is that as long as the coefficients in your equation, these characteristic equations, and the coefficients, that is the coefficient of s square, s, the constant, if all these numbers are real numbers, then the roots can be complex, there can be complex roots, but they will always occur in conjugate pairs. That is, they will be always of the form a plus ib, and there will be also a conjugate a minus ib. Complex roots cannot occur in isolation as long as we restrict the coefficients of the polynomial to real numbers. Okay, so keeping this in mind, for xi less than 1, that is the case when there is an imaginary part in the pole. So in that case, the poles are j. J is again the imaginary thing, 1 minus xi square, right? Now if you draw this one, this case, so this picture will be for xi less than 1. So this is the real, this is the imaginary axis. Let's say we have a root like this, so the real part is given by minus xi omega n. Okay, the imaginary part is j omega n 1 minus xi square, right? And the magnitude. So if you find out the magnitude of these poles, these complex numbers, the magnitude is square root of real part square plus imaginary part square. So xi omega n square, xi square omega n square plus, let me write it, so it will be under root of xi omega n square plus omega n square 1 minus xi square, and this is omega n. So the distance of this point from the origin is omega n, and this angle theta you can see is cos inverse xi. Okay, and since it's a second order system, and as I mentioned, there will be complex conjugate poles. So if one pole is complex, then the other will be same conjugate of that. So the real part will be the same, just the imaginary part will be minus of the first one. So j omega n 1 minus xi square, right? So this is how the poles will look like, and as I told you before, we will denote poles using crosses. And this system does not have any zeros because the numerator is 1, right? So few things to note here. Xi is b by 2 under root km, and most of the scenarios mass is always positive, stiffness and damping is also generally positive. So xi is generally positive, and omega n is also positive. So minus, since the real part of this root, it is negative, right? So always negative generally. So that means that this system will be stable for positive xi and omega n. As long as xi is positive, then the system will be stable because the real part of the root, that is negative. Okay, so let me write down the, so now two poles or the placement of these poles tell us about the stability of the system. So for now we will just take this picture as a reference, and I will draw multiple scenarios which not all of them can occur in this specific system, like the spring mass damper system, but for any second order system, not exactly the spring mass damper kind of system, for any second order system, what are the different positions of poles that can basically happen, and what will be the effect on stability. Okay, so let's
Sir,
see that.
sir,
Yeah, go on.
sir. Here, could you please repeat? So, why did you conclude that it is stable? I mean, xi is negative over here. I mean, xi in
Yeah,
general is
so
positive, but there's a
yes,
negative sign.
I will discuss this. I'm going to discuss the stability criteria. So the stability criteria says that the real part of the, if the real part of the roots is negative, right? So the real part of the root here is xi omega n, right? So if the real part of the root is negative, then the system is stable of all the poles. So for all the poles, if the real part is less than 0, then the system is stable. And why I concluded here that this, the spring mass system, this will be stable, because these quantities xi and omega n will in general be more positive. Omega n is definitely positive, and xi will also be, I guess, most likely will be positive, because I'm not sure if negative damping can happen, I think, but yeah, very specific case. For all practical purposes, you can consider that xi will also be greater than 0, and that's why, so the product of two positive numbers and there's a minus sign, so the real term will always be less than 0, and that's why this system will be stable. Now, yeah, the, did I answer your question first?
So that's the definition, sir. That if the real part is
Yeah. So that's what I'm coming on right now. That's the definition, and I will also give you some intuition on it. So since we are talking about it, let's continue on that only. So you see that these poles, uh, yeah. So these poles are roots of the equations that we solve, right? The characteristic equations. And thinking of the second order system, the thing that we are trying to find out is the response xt, right? To find out the response xt, we transformed it into the from time domain to frequency domain, and then in frequency domain we found out the characteristic equation, and then we found the poles. So thing is that if the real part is negative, then there is an exponentially decaying component in the solution, right? So what we had seen in the last class, that the solution to homogeneous second order differential equations like these, we wrote it as xt is equal to c1 e to the power s1t plus c2 e to the power s2t. No, I mean two roots come, but in general solution is like this. Okay, let me write that. Yeah, if we know that it's a second order system, let's continue with that. So c1 c2 e to the power s1t s2t. If s1 and s2 are the same, then there will be only one term, right? So the idea is that if, so there are exponentials involved, right? There are exponentials involved, that is pretty much clear. Now if the exponent of the exponential, the power of the exponential, if it's positive, then exponential will be growing, right, with time. That is clear. And if the exponent is negative, the exponential will decay with time. So if I draw e to the power x, then how does it look like? It grows with time, right? It grows on with time. And if I draw e to the power minus x, it decays with time, right? Is this clear? Right, so since the solution of the response, right, the response is a combination of exponentials, right? And exponentials can be like this, if, and this is for the real case, and if there is an imaginary component, right? So if there is an imaginary component, then the response is sinusoidal or oscillatory. Okay, so our total solution of that second order system, the total response will be a combination of these, right? A combination of these, either this and this or this and this. No, so the idea is that there should be no component in the solution which is growing with time, right? And that can, we can ensure if the real part of the root is less than 0, because the oscillatory part will definitely not grow. It will just, if it's a pure oscillatory thing, then it will just oscillate with a fixed amplitude, right? It will not grow. The only thing that it can, the only thing that can take the response to infinity is some component which grows with time, and that is the component which can occur only when there is a real positive real part in the root, right? So that's where this idea comes from, that the root should be, the real part of the root should be negative, such that the exponentials that are coming in the solution, they are of decaying nature, right? Is the doubt clear now?
Yes, sir. Yes, sir.
Right. So
Sir, like
yeah.
it should vary very lightly, no, sir. Like if we see this e power minus x graph
Mm-hmm.
over time, as the time grows,
Mm-hmm.
it tends towards zero, but it doesn't become zero. So even it should vary slightly, no, sir. That's when we call
Yeah,
stable.
yeah. So in controls, we want guarantees, right? So we want guarantees that it will not grow, right? That function is bound to be decaying. It is decaying in the sense that if there is a value at, let's say, t is equal to t1, the value is x, then, and if t is equal to t2, the value is x2, then x2 is bound to be less than x1, right? So how fast it goes, that also you can modulate, but the main thing that you can guarantee is it will. And for again, the you can see yourselves that these exponential functions, they grow, that they go close to zero pretty rapidly, right? If and especially if there is some uh, like I just told, e to a minus x, let's say e to a minus 2x minus 3x, they grow, they go close to zero pretty quickly, and for practical purposes that much is enough, right? So the idea is that with time it is decreasing, and that's what we need. There should not be any component that can increase with time, because that's the thing which we can't control then, and it will make the system unstable. So slow or fast is a, you can think like a secondary thing. The first thing is that it should go to zero, which is happening in the exponentially decaying case, right?
Sir, like I said, slightly it should fluctuate, no, sir. It should decrease slightly. So okay.
No, slightly, again, slightly decrease slightly and or rapidly, that is not our concern here, right? So if I put e to the power minus 100x, let's say, then the decrease will be very like it will go to zero much faster than e to the power minus x, right? So both exponentials will decay, but one will decay faster than the other. So that we are concerned about in some cases, but the primary thing that we are focusing is that the output is decaying and it will not grow with time. Either it goes to zero slowly or rapidly, that is a secondary concern.
Yes, sir. Yes, sir. Clear.
Right? So the first is, if real part of the root is less than zero, implies that it is stable. If real part is greater than zero, then there is a exponentially growing term in the solution and it's unstable. So we avoid these situations. We would like to design our system such that the real part is less than zero. And if real part is equal to zero, then we call those system as marginally stable. And these are like pure oscillatory systems, pure oscillations. So in this case, there is only e to the power j omega term, and as I mentioned, it would be oscillating with a fixed amplitude. Okay, so in this scenario, the response, if there is a non-zero imaginary term also, so the response will be uh, exponentially decaying. So it will be like this, right? In this scenario, the response will be exponentially increasing, like this. And in this scenario, the response will be fixed amplitude, right? Fixed. So to put all these conclusions in one diagram, I will just quickly construct a diagram for these systems, and that will help you visualize also and remember also. So this is the S plane, same as before. This is the imaginary, this is the real. So I will draw different pole locations, and what will be the response in that case, right? So first let's see if the pole is negative but on the real axis, right? A second case could be positive on the real axis. Third case can be positive and complex, positive real part with complex number. Fourth can be purely imaginary, and whenever they are complex roots, then there is a conjugate of that also. And this combination final is when the complex roots with negative real parts, right? So in this case, so this is complex root with negative real part. So here, as the real part is negative, so there is an exponentially decaying effect, and since there is a non-zero imaginary part, so there will be oscillations also. So it will be exponentially decaying oscillations. So let me draw the envelope first. Right, so exponentially decaying oscillations in both these cases. That is the first case. Second case, again the root has a negative real part but no imaginary part, so there will be no oscillations. It will be just straight forward decay like this. Okay, this is the second. Now third case, is when it's exactly imaginary. So then there will be oscillations but without any decay, fixed amplitude. Now fourth is this one. So these last two cases, they have positive real parts, so this will grow unbounded, right? And this fifth scenario, they also have a positive real part but also a imaginary term, so there will be oscillations, and the oscillations amplitude will grow with time, so it will be like this, right? Any doubts in this diagram? Okay. Right, so with this information, given any system, you can find out the characteristic equation from the transfer function. From the characteristic equation, you can compute the poles of the system, and by seeing the real part of those poles, you can comment whether the system's response is stable or unstable. So this is one way of commenting on stability of systems. Now we will go to a completely different approach, and a different paradigm for deciding the stability of systems, and that is the Lyapunov stability. So we have a system, right? Let's say we have system x dot is equal to fx. This is the system dynamics, and f is differentiable and continuous. Now in Lyapunov stability, let me motivate it like this, that basically Lyapunov stability constructs a function called as Lyapunov function, which in some sense you can think of it is like resembles something like an energy function. So for the system at hand, you write some sort of an energy function, and the idea is that if the system's energy is decreasing, then we can say that the system is stable, right? So just intuitively thinking, any system in which the energy change is positive, right? So the system is gaining energy, not losing energy, then the system won't be stable, right? It will just drive the output to uh, away from the equilibrium position, right? So think of a pendulum, right? So a pendulum, not an ideal pendulum, a pendulum in the real world, if you just perturb it from its mean position and let it swing, then slowly it comes back to its mean position, which is the equilibrium point, right? And this happens because there is a dissipation of the energy. It loses energy and slowly comes back to the position from where we displace it from. Uh, but in the other case, right? In the other case, where let's say the pendulum, you completely turn the pendulum upside down such that it is like top down, then that is also an equilibrium, but it's an unstable equilibrium. Why it's an unstable equilibrium? Because if you perturb it slightly, even towards even very slightly towards either of the side of the equilibrium point, the synergy of the system will start increasing, and again the system will not come back to the same place. So first, let us just again rebuild the idea of stability. So stability means that, let me draw it figuratively. So let's say a trajectory starts from here, right? And for all time t, and there is a space around this. So let's say this is a space d, and this is x0. Now, if it starts here and stays inside this for all time t, right? For all t, then the system is said to be stable. Okay.
Sir, here you are representing the system as a point, sir.
No, no, not as point. So x0 is the initial state of the system. So that's it's a state space diagram. So basically it's like let's say for the block, right, for the spring mass block, the position, the x position and velocity, they together form the state, right? So the plot will be like the initial conditions. The initial condition will be, let's say, zero position and some non-zero velocity, right? And I will let the trajectory, and this will be the trajectory of the system. What I am drawing is the trajectory of the system, that with this input and the given dynamics, how does the position and velocity of the system change over time, right? So this will be the resulting some trajectory of the system. What I am saying is that if that trajectory remains in a certain bounded area around the initial point for all time t, right? I mean, once you, let's say, perturb it, and then for all the time after that, the trajectory remains in a certain region around the initial point, then we say that the system is stable. And the initial point is what we call as so uh, stability is concerned regarding the equilibrium points, right? So first thing that we will see is equilibrium points. So what are equilibrium points? The place where x dot is equal to 0. That is, if you place the system at that state, then, and if there are no perturbations, then the system will stay there, right? So x dot is equal to 0, that implies that fx is equal to 0. So x such that this, so these points, these x are called equilibrium points, or they are also called as fixed points, right? So the idea of equilibrium is very straightforward, that wherever there is a point where x dot is 0. X dot is 0 means that if you place the system at that point, then the system state will not be changed, because x dot is 0, which is for a pendulum case, it's the bottommost point, right? If you place it precisely there, the system will not move from there. Okay. Now equilibrium points can be of three types, right? It can be stable, it can be unstable, and it can be a saddle. So again, I will not go into very rigorous mathematics of these, but I will motivate and intuitively give you an idea. So stable equilibrium systems, and thinking of the variation of x. So if this is the plot of x, then x dot is 0 here, right? Here x dot is 0. And if you perturb the system slightly to the either side of this point, it will come back, right? Because the point that we have has some special characteristics which you will see, which make it stable. So trajectory is starting, if there is a system at that point, this type of point, and if you perturb it, then the system will return back to the equilibrium point, right? The second case can be like this. So here also x dot is equal to 0, but if we perturb it slightly, then the system will not come back to the equilibrium position, right? it will it will go to another state. So basically in pendulum's case, if you somehow manage to keep it here and slightly perturb it, the system will quickly go to its stable equilibrium point, which will be down below, right? So that is unstable equilibriums are those points from where if you perturb the system, they won't come back to that equilibrium point. And the third is the saddle point. So saddle points is like a half of both the stable and unstable world. It's like so plots like these, in which at this point the slope is 0, x dot is 0, but there is no guarantee like either depends on which side you displace it, it behaves differently, right? So if this is a scenario, if I displace it slightly towards the right, it comes back, but if I displace it slightly towards left, it goes away, right? So in a sense, saddle points are also not stable, right? So the only case that is like we wish to have these cases is the stable one, right? In which all the trajectories which start from that equilibrium point come back to that equilibrium point. So, and this type of stability is called asymptotic stability. Okay, so just stability is staying in the region, asymptotic stability is coming back to the equilibrium point, right? And yeah, so that's the difference. And there are a few other terms also, like depending on how fast you go towards the equilibrium point. Now in all these subsequent discussions, whenever I write x is equal, I will always write x is equal to 0 as the equilibrium point, or call it as the origin. So that should be fine, because let's say if your equilibrium point is not at always at origin but at some non-zero point, but you can always shift your frame, your coordinate system there to that non-zero equilibrium point and then start saying it as the origin, right? So all that discussions holds, whether irrespective of whether the origin is actually the equilibrium point or some other point is the equilibrium point. Okay, so coming back to Lyapunov stability.
Sir,
Yeah.
just a small clarification.
Yes.
Over here. Here the parabolic curve you have drawn, sir. Those are the x. Those are the x values, sir.
Yeah, x values, x and t.
Okay. Yes.
Is x and t. And the slope will give x dot. So at the bottom x dot is 0. So that means it's an equilibrium point. And intuitively, as we saw, because if you deviate from that equilibrium point, it comes back to the same point. So it's a stable equilibrium point. Okay. So now Lyapunov stability gives us a recipe, to find out that in a given region whether the equilibrium point is stable or unstable or saddle, right? So it says about stability. So let's first write down the criteria. So firstly, whatever we will see is for local stability. So again, these are terms which need to be understood in depth, but local stability means that the conclusions which you will draw will be restricted to a certain region around the equilibrium point and might not be applicable through the entire domain of the states, right? So it will be like if you start in this region, then it's stable, but if you go outside that, then it may not be stable, or those results might not hold. Okay, so it starts like this. So we have a system x dot is equal to fx, then and a region we will define a region D around origin, that is x equal to 0, and that is an equilibrium point, let's say. Okay. So now let's say there is a function Vx, and that is a scalar function which is continuously differentiable. So these are few characteristics which need to be satisfied. So Vx is a scalar continuously differentiable function, and Vx should have certain properties, should satisfy certain properties. First is that Vx is greater than equal to 0 for all x belong to D, and V0 is equal to 0. This is the first criteria. Now the second criteria is about V dot x. So V dot x should be less than equal to 0 for all x belonging to D except 0, and at 0 it should be 0, right? Then if these conditions are satisfied, then we can comment that x is equal to 0 is a stable point in the sense of Lyapunov. It's a way of saying these, that since we are using Lyapunov theory for commenting on the stability, so we say that x0 is stable in the sense of Lyapunov. Now let's unpack these conditions one by one. So first thing is that Vx is a scalar function. Okay, so output of x could be a vector, but output of Vx should be a scalar, and that quickly gives us an hint that we can relate it to energy functions, because energy is also scalar quantity, right? Now the first criteria is Vx should be greater than 0 when evaluated for all x in that domain. So the main thing here is that, and that's what we solve for in problems, is we have to construct this Vx will not be given to you, but with some intuition, experience of solving questions, we have to construct such a Vx. And first we have to satisfy the property in point 1, that Vx is always greater than 0, and at x equal to 0 it is 0. And then we differentiate Vx, and if it satisfies the second set of property, that it is less than or equal to 0 for all points in the domain, and at x equal to 0 it is 0. If second point is satisfied, then we can comment that x is equal to 0 is a stable equilibrium point. And with just this we can say stable, and if we impose a harder or a more strict condition on v dot x, if v dot x is strictly less than 0, no equality for all x belonging to D except 0, then it's asymptotically stable. Right? So the difference between just stable and asymptotically stable is that in the just stable case, it is not guaranteed that the system state will return back to x equal to 0. Right? It will stay in that region, but not necessarily it should come back to x equal to 0. But for asymptotically stable systems, it is guaranteed that the system after some time will come back to x is equal to 0. That is the asymptotically stable system. Right? So let's, any doubt still here in the conditions of the Lyapunov stability criteria?
sir, if it won't come for the stable case, sir,
Mm-hmm.
like when it is not strictly zero, that v dot x is not strictly zero, we call it stable, no, sir, according to Lap and you. Uh, sir, if it doesn't come to zero, will it be like will it not cause any, like, can we analyze it, sir, at that? I mean, can we? Is it safe to use at that
Yeah,
condition, sir?
I mean, it depends. So there will be few more things. Like if so the associated thing is the region around the point which you are considering, right? So if the region is small enough, and if you are like talking about some practical sense scenarios, if the region is small enough and you can work with your state being in that region, right, that it's fine. But in you're right that in most cases we go for asymptotically stable, designing asymptotically stable systems, that it basically the error goes to zero. An error will go to zero. I mean, by error here I mean that the state will approach the equilibrium point or the reference point, uh, and make that difference go to zero. So we try to design systems which are asymptotically stable in most cases.
Okay, okay, sir.
So yeah, getting asymptotic stability is very nice, and if we get that, well and good. Yeah, so this a few terminologies which you will encounter whenever you study uh, Lyapunov stability is like positive definite and negative definite, and similarly semi definite, and similarly negative semi definite. So this kind of a symbol is used to denote positive definite. So positive definite means that it is always positive in this case. Positive semi definite means that function which is either 0 or positive. Negative definite is opposite of that. So either negative definite means strictly less than 0, and negative semi definite means it can be 0 also and less than 0. So you can say that the Lyapunov function should be a positive definite function, and its derivative should be negative semi definite for stability and negative definite for asymptotic stability. Okay, so let's take an example. So let's take an example of a pendulum. Here this is the equilibrium point, right? Theta equal to 0. This is theta. So I think you guys are familiar with the equation of motion of the pendulum. So ml square theta double dot plus mgl sine theta. Now till here you would be familiar, and this is the standard case when there is no energy dissipation, right? So this is the ideal case when if you swing the pendulum once, then it will keep on swinging. But here I will add a dissipation term, a damping term. So this is same as the terms which you have seen in the spring mass damper system, b times the velocity. So this is our system. So damped pendulum, it's a damped pendulum. Now let's propose a function. And this case is commonly used because here the function that we will use is exactly the energy of the system. So if you see closely, this is the kinetic energy term and this is the potential energy term, right? So this is our candidate. What is this? This is the candidate Lyapunov function. So in Lyapunov stability, as I mentioned, we construct such a function and we try to find a function which satisfies those criteria. So if we find one, then we can say about the stability. But let's say if you don't find one, then you know we have to prove that the system is unstable. We might have to take other ways. Okay, so let's say if this function satisfies all the criteria or not. So if first thing is that this should be positive, right? So this is the energy, so this will always be positive. And E00 is I think first term is 0, second term minus mgl. So fixed thing minus mgl, you can always change, we can always change the reference such that this point is the 0 point. So if we write from this point, the potential energy is mgl 1 minus cos theta. So let's write like that only. Okay, now so E00 is 0. Now let's find E dot. So how will you find E dot? E dot we can find by differentiating E with respect to the states. Here the state is basically x is equal to theta and theta dot, and fx. But okay, let's not do like this. So let's start differentiating. The first term is half m l square, then theta dot square, so 2 theta dot and theta double dot. So this is first we differentiate with respect to theta dot, and then we differentiate theta dot with respect to time, right? Plus mgl and 1 minus cos theta. So minus cos theta is sine theta, right? Sine theta and theta dot, right? Okay, this is the thing, isn't it? mgl, 1 is gone, minus cos theta is sine theta and theta dot. Now let's cancel this 2 and 2 here. Let's take out theta dot as common. The term inside is ml square theta double dot plus mgl sine theta, right? And what is this inside term? It's from the equation of motion, we see that this is b theta dot, isn't it? So this term is b theta dot square. Okay, so our e dot is minus b theta dot square, and this is less than equal to 0 for all theta dot, isn't it? And does not depend on theta, so just theta dot, because theta dot square is always positive. B we are taking as positive, so minus b theta dot square is less than equal to 0 for all, right? So in this case we say that the system is stable. Now to prove asymptotic stability, there is one more theorem that we use, the LaSalle theorem. LaSalle theorem is, again I will just briefly mention. So this implies stability, right? This implies stability because we are not saying that this is strictly less than 0. Yes, go on.
Sir, so the from this we proved that the pendulum loses and gains minus b theta dot square energy, no sir? That's what we have proved here, sir.
Yeah,
Like
not gains, loses. E dot is always less than or equal to 0. So rate of change of energy is less than 0. So it will lose energy, not gain energy. And
okay.
that's why it is stable.
Yes, yes.
Yeah. So at this stage, you can just comment that this system is stable. But as we discussed a while ago, that we are more interested in knowing if the system is also asymptotically stable, right? So that is very obvious if your E dot comes out to be strictly less than 0. But in this case, it comes out that it can be equal to 0 also. So the LaSalle theorem says that it is again I will slightly try to put it in a simpler term. So the idea is that if E dot is equal to 0 and the Lyapunov's stability criteria is satisfied, Lyapunov the two properties is satisfied, and the third thing is that if energy increases if the states are also increasing, right? So let me again write down the general statement. It's that if x is equal to fx and vx is positive definite, v dot x is negative semi definite, right? And the third thing is vx goes to infinity as x goes to infinity. So this means that the energy of the system increases only when the norm of the state increases. So in this case, if this is satisfied, then x, the state, converges to the largest set where v dot x is 0, right? So if these three things are satisfied, then x will converge to the set where v dot x is equal to 0. So in the pendulum case, my E dot is minus b theta dot square, which is negative semi-definite. So as soon as it becomes negative semi-definite, I will try to invoke Lassalle's theorems to check if I can prove asymptotic stability. So what you need to check is, this criteria satisfied, this one. So Vx tends to infinity as norm of x tends to infinity. That means x and x dot become very large, then v should also become very large, which is the case here, because theta dot, if theta dot is large, then this term will be larger, right? So this will take it towards large values. The second term is will not affect because this is a cos theta term, so it will remain between -1 to 1, but the kinetic energy will increase obviously. So this new property is also satisfied, and then we can conclude that x converges to the largest set where v dot x is 0, and in our case, in the pendulum case, e dot is 0. So here set is mentioned because e dot is equal to 0 can be possible at many points, more than one points, but here that point is theta equal to 0, and theta dot equal, theta dot equal to 0, right? So for theta dot equal to 0, this will go to 0, right? And theta equal to 0, theta dot equal to 0. So the point, this point, so this means that this set that we are talking about here in this theorem, this contains only one point here, right? So the idea is that that's the point which the trajectories will converge, and since there is only one point, so it automatically becomes a case of asymptotic stability. I think there might be some confusions here because this is slightly uh, not very straightforward, the Lassalle's theorem. But so the points to keep in mind is that the Lassalle theorem will be invoked whenever we want to comment on asymptotic stability of a system and the E dot or V dot comes out to be negative semi-definite. In some cases, what happens is that E dot is 0 only at only one point, and that's the point which we want to test for asymptotic stability. So it automatically gives us the proof that that point is asymptotically stable. So so I will stop discussing the theory part here and quickly discuss few basic questions based on these concepts. So the first is to prove the stability of a system using Lyapunov method. What type of function that we construct? So we construct an energy function, right? That is the Vx, which has to be positive definite. Right. Second question is, if Vx is an energy function, then Vx has continuous first partial derivatives, right? And Vx is greater than 0 for all x except at what's this question? Yeah, V0 is equal to 0. This is the criteria which we need to satisfy. No, this is the point which I was saying. To prove the stability of a system where V dot x is equal to 0, what's the theorem that we use? We use the Lassalle's theorem. And that's where we find out what are the points where V dot x is 0. And if that point contains only one point, that there is only one point in the domain where V dot x is 0, then that point automatically becomes a asymptotically stable point, even if V dot x is not strictly less than 0. The fourth question is, using the Lyapunov's method, we wish to prove the stability of a spring mass damper system, right? The choice of the energy function could be, so and the answer is in the question itself, that it's hinting that we should formulate an energy function. So for the spring mass system, the block has a potential energy due to spring and a kinetic energy, right? So the first option seems correct. It's the kinetic energy term and it's the potential energy term. So this is the correct answer.
Sir,
Yes, Karthik.
uh, uh, here, sir, in the spring mass damper system,
Hmm.
mx dot plus bx dot plus kx is equal to 0, no, sir?
Hmm.
In place of 0, when do we write f, sir?
Yeah. So F is we write whenever there is an external exciting force on the system. Let's say, imagine that you are on a swing, and there is a person behind you who is in each cycle when you go back, uh, he or she pushes you, applies a force on you. So that's one kind of a oscillatory motion in which there is an external exciting force also, right? So there are many, like most of the cases, it's this scenario only, that there is some external excitation also. So it could be like you are in the spring mass system, I just apply an impulsive force at the very beginning. So the the equation of motion in that phase will have an F also, right? Or if let's say you are I would give an example. If let's say you are modeling the suspension of a vehicle, right? So suspension in a vehicle in which, let's say, the suspension is modeled as a spring and damper, the wheel, and this is the road. So there are some forces coming here, right? Some forces coming here, and this the function of this spring damper system is to basically reduce the forces experienced by the passengers, right? So these kind of systems, in these are systems in which there is an external force acting on the spring mass system, and it's not just the free spring mass system doing its natural oscillations. So in most practical applications there will be an excitation, there will be some force, external force, or some external displacement also. So yeah, did I
So the
answer you?
sir, so that force will be opposite to the force that is formed by mx dot plus bx dot plus kx, sir. It should be opposite, no, sir? Like,
No, why opposite? That force can act in any direction. It's not restricted by the spring. Will accordingly, the spring will the spring force will act accordingly depending on the displacement, and the damper force will act according to the velocity. But the force, it's like you can there is a spring mass system, and you can apply any external force on it, whether it's towards left, towards right. You can pull it or push it. That's There is no restriction on the external force that can be applied on the system.
okay, sir. So the okay, sir. Okay, yeah.
Yeah, that's what I said. Like the spring and the damper, that they will generate the force depending on what's the displacement and velocity at a certain point in time, right? Let's say if the spring is compressed, then the spring will produce a force pushing the block away, and similarly if the spring is elongated, it will try to pull the block towards it. So no restriction on the external force.
Okay, sir.
Right, so the next is that in a two input control system for a robot link, the combined transfer function, how can we obtain that? So the way of doing that is superposition way, in which we assume zero input uh, to one of them, and then solve for the other, and then put zero input in the first one and then solve for the second one. So since these systems can be treated separately, so we can use the superposition type of an approach. Now, this seventh is related to something which I have not discussed in the discussion hour, but of course, it has been discussed in detail in the lectures, is the actuator dynamics. So, basically, motor and its circuitry and modeling it as a second order system. So, all those things have been discussed. So, we know this relation that the torque produced by the motor is directly proportional to the current input, right? The armature current. So proportional to the armature current, right? And the equation that we write, the RL circuit, is this equation, right? This is a motor inductance, and this you would remember from the lectures. This is the applied voltage, this is the back EMF of the motor, this is the resistance, and this is inductance. So this is a voltage balance of this circuit, in which there is a source, then there is inductance, then a resistor, right? And here is the motor, and here is the back EMF, and we get the motor torque here, and the position, right? So and the eighth question is also related to this only, that the total voltage acting in the armature DC motor is applied voltage minus back EMF voltage, right? So V minus VB. So back EMF voltage is in opposite direction of the applied voltage. So we take the difference of these two voltages, right? So I will just quickly summarize what we have seen today. So we saw the second order system and how to model it as a transfer function, right? Then some general notes about transfer functions. Transfer function gives the relation between the input and the output, right? And generally expressed as ratio of two polynomials in which the degree of the numerator is less than the degree of the denominator. The denominator, when equated to 0, gives us the poles of the system, and the numerator equated to 0 gives us the zeros of the system. And the poles of the systems are further they tell us about the stability of the system, because at a pole the system output goes to 0, and the poles, again, for the second order system or for any system, the poles can be real and complex. If they are complex, they occur in pairs, complex conjugates. And if the real part of the pole is less than 0, then if all the poles have real part less than 0, then the system is stable, right? If there are poles which have positive real part, then the system will be unstable, because there will be a component of there will be a component in the response which will be exponentially increasing, and so it will become unbounded with time. And if the real part itself is 0, then the root is purely imaginary, and in that case the output is a pure oscillatory output without any exponential decay or growth. So it will just keep oscillating with a fixed frequency, right? So we drew these diagrams, the different scenarios that can arise. So if the pole is exactly on the real axis, then there is no imaginary part. No imaginary part implies that there are no oscillations, so it will be a uh, typical exponential growth or decay. And if both real and imaginary parts are non-zero, then it will be either a exponentially decreasing oscillatory response or exponentially increasing oscillatory response. Then we saw Lyapunov stability. So in Lyapunov stability, we propose a function, the Lyapunov function, which satisfies certain criteria. It is positive definite in the entire region, it is 0 at the origin. And if the derivative of the Lyapunov function is negative semi-definite, then the system is called stable. And if it is strictly less than 0, that is if it is negative definite, then we can say that the system is asymptotically stable, right? So yeah, so that is what I had planned for this discussion hour. In the next one, we will discuss the independent joint control and feedback linearization, in which in which Karthik, which in that time I will discuss your. You can ask your doubt again, and I will discuss that.
Okay, sir.
Okay, then if there are no other doubts, then I will wrap up for today.
Uh, Sir, I have some
Yeah, yeah,
clarification.
you can go ahead.
Oh, yes, sir. Could you show the screen, sir? Yeah.
Yeah, yes.
Scroll up, sir. The controlled system block diagram.
This one.
Yes, sir. So this is a closed loop, no, sir.
Yeah,
So,
this is closed loop.
sir, here we give while the comparator, sir, it will take into account of output also, no, sir. Well, like it compares the input and as well as the a part of output also, no, sir.
Yes, yes,
While
yes,
making decision.
yes.
So when we give first time, sir, when we are giving an input first time,
Mm-hmm.
at that time, how will the comparator compare, sir? Like because there won't be output at the very first time, no, sir. So
Yeah,
in
yeah,
that
yeah.
time, how does
Yeah,
it take
so
decision?
yeah, that's a good question that could arise. Uh, yeah, so that time there will be no estimate of the output, and it will be just maybe what's the value that you initialize it with, which will be most likely be zeros. So for the very first time, you send some, because to start things off, you need to first send an input, right? So you will need to send an input first, just an input, to start getting some output, right? So the very first time, yes, you're right, there will be no inputs, and it's not that without, if there is no feedback from the output, some control input cannot be generated. It will be generated, right? It's like it will be xs minus 0, so es will be equal to xs, and it will go ahead like that. And once that system dynamics happens, there will be some output, and then the process will start. So yeah, it works like this.
So we can directly take it as zero, sir. Like because in some systems, I mean, I'm not sure about those systems, but like in some cases, zero is considered as a value, no, sir, than nothing. So it's
uh,
uh,
like
uh,
mathematically the form, like when you will program these things, right? So mathematically the very first thing, or the first yeah, or the first state that you can think of is that uh, you can initialize both input and output to the same value, right? So it's like something like this. So where is the, yes, so it's like let's say, yeah, I mean, let's say there is this 2R thing, and so this is the position from which let's say we start implementing our control. So we know this position, right? So we can uh, the theta input and theta output, all we can set to some value of theta that is there, right? And then we will start giving our trajectory. We will give new theta input for the first time. The control will generate some torque, it will be applied, and then we get the updated theta output, and then the loop will start. So you can do like this also, initialize both input and output to the value at, the value, the states at that, let's say your initial states basically. If you know that, you can both initialize both of them with that value.
yes, sir. Got it, sir. Uh, so the one more part is similar to this, sir. This
Mm-hmm.
question, sir. Uh, like the actuator, sir,
Mm-hmm.
stepper motor,
Mm-hmm.
DC motor, um, and some other actuators, sir, all
Mm-hmm.
can be worked in open loop, sir.
Yeah, so
With all,
stepper motor works in open loop. uh, Servo motors work in closed loop. The normal DC motors,
Sir, you complete with this, then we will come to that.
yeah, yeah. So stepper motors work in they work itself. They they work in open loop only, right? And the servo motor, the way they work, they have inbuilt like a system to control the position or the velocity. So servo motors worked in closed loop. DC motors also. Can you work it as in open loop just as? Yeah, I think you can work a DC motor in open loop.
sir, so if a actuator works in one system, doesn't mean it works in another system, sir. Like if it works in open loop, doesn't mean it works in closed loop, sir.
It depends like what are the components you are considering when you say actuator, right? So when I say actuator, so I also think that there is a circuitry behind it in which is like controlling the amount of current which is flowing at the very low level. So if you are splitting that also, then you would say that okay, that's just open loop, that you are sending some let's say you are sending some velocity value that is being converted into some current value, and that current is being applied. But in many of these motors and all, there will already be a inbuilt some circuit which will do that closed loop thing already. So from practical point of view, uh, I think open stepper motor is maybe the most common way in which if you wish to do open loop control, you would do that.
Okay, so we cannot generalize, no, sir. Yeah.
No, I think we cannot.
Okay, sir. Okay. Thank you. Thank you.
Yes, what's the question? For transfer functions, we opt for zero initial conditions. Can you explain, like, can you just elaborate your question more?
Sir, in this 2R diagram, you have shown theta
Mm-hmm.
equal to theta naught,
Mm-hmm.
kind of initial condition.
Mm-hmm.
So do we take that itself as zero, or theta dot?
Right. So as I mentioned, like uh, these things won't change, won't affect the system much. The system, in the sense that it's all a kind of a reference thing. Zero, if you consider it as zero, you that's good to go. If your zero reference is somewhere else, then this will have some non-zero value. But the main thing that will be you will concerned while designing the control system is that what's the transfer function, and transfer function of this, right? So it won't depend on, like, in this block diagram that we draw, right, or in the equation of motion that we write, we don't describe the initial conditions. Initial conditions will, if in some cases, yes, affect the response of the system. Let's say there is some in the spring mass system, let's say there is some initial velocity or initial force. In those cases, that will affect the system response, and there can be like other ways to include it. But in the context which I mentioned, either you set it as zero or some known value, let's say 30 degree, 60 degree, it won't affect the way the control will proceed, because that's just a fixed value. You can always offset that, right?
Okay, sir.
Okay,
So whatever we take, it is just for reference, sir. Then.
Yes, yes. Like in these things, you can set your reference, right, and the reference is always a choice of the, the user or the programmer. Set, okay, in the 2R case, you would choose some convenient position. If this is it, so maybe the position in which the link is lying flat, both the links. Maybe we choose that as the position in which we set we say that theta 1 theta 2 both are 0, and then take or measure angles with respect to this reference, right? But it's entirely up to my choice. Like I want, maybe if I want to do something different than this, or maybe this is the position in which I want to keep in most of the cases, so I may consider this as the my zero position, and then measure corresponding with respect to this place, right? So these things are just these are fixed things and just a choice of the person, basically. It will not affect the analysis that we do subsequently.
Yes, sir. Got it, sir.
Okay, then thanks for joining, and we will meet in the next week.
Thank you, sir.
Thank you, sir.